In this problem, we'd like to find the volume if the region is enclosed by y equals x squared, y equals 0, and x equals 2. So again, let's just sketch up a picture. Y equals 0 is the x-axis. X equals 2 is the vertical line. And y equals x squared is this parabola. So these things all intersect in the first quadrant, and so we're focusing on this area here. And in part A, the axis of revolution is the x-axis. So in terms of our picture, the whole thing is being revolved in this direction, which means our circles are lined up horizontally, and we'll want to integrate everything in terms of x, or at least that's a way to think about it. So first, let's talk about big R. I'll do that in red. Big R is the distance from the outside of the piece to the axis of rotation. So big R in red will be x squared, and there is no little r, there is no inside. And the shape of what we're integrating when we're done is going to look something like this. And so we've got all these circles. So we're going to integrate, and we're just finding the areas of circles and adding them up. We'll integrate from 0 to 2, and our radius is x squared in this case, so we want to integrate x squared squared, because the area of a circle is pi r squared dx. And switching back to black, I'm going to clean this up just a hair. This is just like integrating from 0 to 2 x to the 4th dx, which we know is going to be pi times 1/5 x to the 5th from 0 to 2, which is pi times 32/5 minus 0, and so our volume would be 32/5 pi units cubed in this case. I'll set up part B. So in B, what's changed is our axis of rotation, instead of the x-axis, is now the horizontal line y equals 4. So we're just taking the same region, this region here, and we're rotating it up here. Our circles will be aligned horizontally. Our object is going to look kind of strange. It'll look something, do the best I can, like this. So it's going to be missing this piece, but still all of these circles. And so our circles are organized horizontally. We'll want everything in terms of x. Our outer radius I'll do in red, or our big radius. Our big radius is from here to the axis of rotation, and that would be 4 units. Our inner radius I'll do in blue. It's going to be this component here, and our inner radius is the whole large radius 4 minus this piece, and that piece in green is x squared, so our inner radius is 4 minus x squared. And so when we set up our integral, it'll be pi times, everything's in terms of x, so we'll be going from 0 to 2. It'll be our big radius, in this case 4 squared, minus our little radius, in this case 4 minus x squared squared dx. If I clean this up a bit, this will be the integral from 0 to 2 of 16 minus 16 minus 8x squared plus x to the 4th dx. And that cleans up pretty nice to simply be the integral from 0 to 2 of 8x squared minus x to the 4th dx. and integrating, we would end up with pi times 8/3 x cubed minus 1/5 x to the 5th, and from 0 to 2. I'm running out of room, so substituting in 2, this will be pi times, when we substitute in 2, that'll be 64/3 minus 32/5 minus, when we substitute in 0, we'll just get 0. And cleaning this up, we end up with 224/15 pi units cubed. Let's move on to example D with this, where the revolution is the y-axis. So again, starting with our picture, we're having the area that's enclosed by y equals 0, the x-axis, x equals 2, this vertical line, and y equals x squared. And this time we're revolving it around the y-axis. So it's taking this piece and revolving it just to the left, so to speak. This means that we'll have a figure that might look something like this. I'm done. But that figure is going to have, it's almost like a very oddly shaped bowl. It'll be missing a piece in the middle. Notice this means that our circles are organized vertically, and so we'll want everything in terms of y. So a couple things. This means that our original curve, if y equals x squared, and that same curve is x equals the square root of y. So if we start with big R, and again I'll do that in red, from the outside to our axis of rotation is a distance of 2. Little r, which I'll do in blue, is from this curve to here, and little r then in that case is the square root of y. And these things intersect at the point 2, 4. That means our stack of circles is 4 units high, so when we integrate, again it's just pi from 0 to 4, because we're doing everything in terms of y, of 2 squared minus the square root of y squared dy. And cleaning this up, our integral is simply the integral from 0 to 4 of 4 minus y dy. And when you integrate that, we've got pi. This would be 4y minus 1/2 y squared from 0 to 4. And substituting in 4, we'll have 16 minus 8 minus, substituting in 0, we'll just get 0. So our volume is 8 pi units cubed. Let's do one more. We'll do the line x equals 4. As our axis of rotation. So this changes our picture just a bit. So it's still the exact same region. This region here. But this time we're rotating it around x equals 4, which is over here. So this will be a weird shaped thing. It'll have a hole in it. It's going to look something like this. It's maybe like one of those small soccer cones you may have seen. I'll have a hole here in the middle. Maybe something like that. It was a rough sketch. But again, the big issue is that our circles are organized vertically, so we'd like everything in terms of y. Big R, which I'll do in red, is the outer distance, so it's from here to our axis of rotation. Well, this entire distance for our axis of rotation is 4, and we need to subtract out this piece right here, which is the square root of y. So big R is 4 minus the square root of y. Little r, which I'll do in blue, is the distance from here to there, which is just 2. So we've identified big R and little r, our big radius and our little radius. So when we integrate, we'll be integrating from 0 to 4 of 4 minus the square root of y squared minus 2 squared dy. And cleaning this up just to make the integration a little bit simpler, this will be what? 16 minus 8 y to the 1/2 plus y minus 4 dy. Taking it one step further, and again I don't have to do this, I just am. This is y minus 8 y to the 1/2 plus 12 dy. When we integrate this, we'll end up with 1/2 y squared plus minus, so let's see, this will be y to the 3/2 and 2/3, minus 16 thirds plus 12y from 0 to 4. Substituting in 4, this will be 8. Let's see, 4 to the 3/2, so square root of 4 is 2, so it'll be 8. And 16 times 8 is 128, so minus 128 over 3 plus 48 minus, when we substitute in 0, we'll just get 0. And cleaning this up, we end up with 40 over 3 pi units cubed. So the idea is still the same, just the picture of what we'll end up with, it ends up being different if you use a square or a square root function. But the idea is still trying to identify what's the big radius, what's the little radius, and we're always just integrating an area formula, the area of a circle in this case.